Assalamualaikum and good day everybody. In this video, we will continue with 2.2 quantum mechanics, sketch 3D shape of S, P and D orbitals, and then 2.3 electronics configurations, explain Upper principle, Hans rule and Pauli Exclusion principle, and justify anomalous electronic configuration of copper and chromium. Without wasting our time, let's sketch the shape of S orbital. The S orbital is spherical shape with nucleus at the center. Let's together we sketch this S orbital. Draw the x-axis, y-axis and z-axis. Then we draw a circle around this axis. Shade the area inside the circle so that the axis disappear. So this is how we sketch the S orbital. S orbital, it has only one orientation since elemental quantum number is 0 and magnetic quantum number also 0. 2 S orbital is larger than 1 S orbital. We can see that the S orbitals larger as principal quantum number increase. Let's continue with P orbital. P orbital has two regions or lobes on either side of nucleus, dumbbell shaped. There is 3 P orbital, Px, Py and Pz. Let's sketch the shape of P orbital. First, draw the axis. Let's say we want to sketch Px orbital. Draw lobes on the x-axis. Shade the area inside the lobes to hide the x-axis. So we have finished sketch the Px orbital. Let's continue sketch Py orbital. On the y-axis, we draw a loop. Shade the area inside the loop to hide the y-axis. So we have finished sketch the Py orbital. Let's sketch Pz orbital. Draw loops or dumbbell on Pz axis. Then shade the area inside the loops to hide the z-axis. Now we have finished sketch the Pz orbital. So we have sketched Px, Py and Pz orbital. Remember that azimuthal quantum number for P orbital is 1, while the magnetic quantum number can be either -1, 0 or +1. And as principal quantum number increase, actually the P orbitals gets larger. As a reminder, Px orbital lies along the x-axis, Py lies along y-axis, and Pz lies along z-axis. These 3 orbitals, they are identical in the size, shape, and energy. The magnetic quantum number value for these 3 orbitals either -1 or 0 or +1. There is no simple relation between the value of m and the x, y, and z direction. For example, the 2px orbital can take the magnetic quantum number value -1 or 0 or +1. Next orbital is d orbital. D orbital has azimuthal quantum number 2. Magnetic quantum number is -2, -1, 0, +1 and +2. D orbital has 5 orbitals with different orientation, namely as dxy, dyz, dxz, dx² minus y², and dz². dxy, dyz, dxz, and dx² minus y² is cloverleaf shape, while dz², it has quite different shape. It has 2 major loops lie along the z-axis and donut shape at the center. Let's learn how to sketch orbital D. Let's say we would like to sketch dxy orbital. Because this is dxy, draw the x-axis and y-axis first. Next, draw the major lobe at the area between x-axis and y-axis. Next, draw the z-axis with headed first. Another z-axis is hidden by the lobes, so we remove the line in the lobes. Let's draw the next orbital D, which is dyz. YZ means the lobe is between y-axis and z-axis. Thus, draw y-axis and z-axis first. Draw the lobes between the area y-axis and z-axis. Next, draw the x-axis from the center to the head of the x-axis. The next part of the x-axis are hidden by the shaded lobes. Thus, we cannot see this axis until the end of the lobes. So, we have finished sketch orbital dyz. Let's sketch orbital dxz. Xz means the lobe is between x-axis and z-axis. Draw the lobes at the area between x-axis and z-axis. Draw the y-axis from the center to the head of the y-axis. Another part of the y-axis are hidden by these shaded lobes. We cannot see this y-axis until the end of the shaded lobes. So we have finished sketch orbital dxz. The next orbital is dx squared minus y squared. X squared minus y squared means the lobes on the x-axis and y-axis. Thus, let's draw the x-axis and y-axis first. Draw the lobes on the x-axis. Since the lobe on the x-axis, erase the line in the lobes. Next, draw the lobes on the y-axis. Since the lobes on the y-axis, erase the line in the lobes. Next, draw the z-axis. So we have finished sketch orbital dx squared minus y squared. The last one, orbital D, is dz squared. dz squared is quite different from the other d orbital because it consists of the lobes and the donut-shaped region. Hopefully, tips show later will help you to sketch dz squared orbital. First, let's draw donut. Next, draw two lobes in the donut. Imagine this area. Donuts hide the lobes. Thus, erase the line of the lobes. While this area, lobes hide the donut. Thus, erase the donut line. Then we draw the x, y, and z axis. To draw the x-axis, start from the center and stop at the donut. Then continue from this point outwards. Another part of the x-axis begin from the center towards the donut, stop right there, and begin from this point going out. Drawing the y-axis quite similar with the x-axis. Starting from the center towards the donut, stop right there. Starting from this point, going outwards, and label as y. Another part of y-axis starting from the center towards the donut, and stop right there. Then continue from this point, going out. Z-axis also has two parts, going up and going down. Both axes going up and going down are hidden in the loops. Thus, the going up is starting from this point and then going up like this and labeled as Z. Downward axis starting from this point and then going down like this. Congratulations, you have sketched dz squared orbital. Let's we have some example. What is the difference between 2px and 2py orbital? This is 2px orbital. And this is 2py orbitals. These two orbitals are identical in size, shape, and energy. But they differ only in their orientation with respect to each other. And for enhancement, please do this exercise. Sketch the shape of 2px orbital, 2pz orbital, 3dxy orbital, 3dx squared minus y squared, and 3dz squared orbitals. Let's continue with topic 2.3 electronics configuration. In this lesson, we will be able to explain Aufbau principle, Hans rule, and Pauli's exclusion principle, and justify the anomalous electronic configuration of copper and chromium. What is meant by electronic configuration? Electronics configurations describe how electrons are distributed in the various orbitals in the principal shell and subshell of the atom or ion. There are three rules for assigning electrons to orbital. Number 1, Aufbau principle. Number 2, Pauli's exclusion principle. And the third one, Hans rule. The first rule for assigning electron to the orbital is Aufbau principle. Aufbau principle states that electrons fill the lowest energy orbitals first and the other orbital in order of ascending energy. Diagram below arrange the orbital according to their energy. The lowest energy orbital is 1s, followed by 2s. 2p orbital has higher energy than 2s orbital. 2p orbital has 3 boxes. 3 boxes here represent 3 orbitals with same energy level. It means that 2p orbital has 3 degenerated orbital. The next higher energy level orbital is 3s, then 3p, after that 4s, after that 3d, 4p, 5s, and 4d. This diagram also can be used to determine the energy level of the orbitals. To construct this diagram, begin with the first energy level, only one orbital, which is 1s. And then the second energy level, it has 2 orbitals, which is 2s and 2p orbital. The third energy level, it has 3 orbitals, which is 3s, 3p, and 3d. Now we can guess how many orbitals in the fourth energy level. Yes, it has 4 orbitals, which is 4s, 4p, 4d, and 4f. And last, for the fifth energy level, we have 5s, 5p, 5d, and 5f. Let's withdraw rainfall to this diagram. The first arrow like this. So this is the second arrow, the third arrow, the fourth arrow, and so on. This arrow look like a rainfall, is it right? The first rainfall falls to the 1s. It means that 1s is the lowest energy orbital. The second rainfall falls to the 2s orbital. It means that 2s orbital is the second lowest energy orbital. The third rainfall falls to the 2p and then 3s. It means that 2p orbital higher energy level than 2s and then followed by 3s. The fourth rainfall falls to the 3p orbital and then 4s. It means that the next higher energy orbital is 3p and then 4s. Alright, can you guess the next higher energy orbital? Yes, it's starting from the 3d, next is the 4p, and then 5s. Let's say we want to fill up the 5 electron in X atom in the orbital as an example. The lowest energy level orbital is 1s, followed by the 2s, and then 2p. One orbital can be filled up by 2 electrons only. 1s orbital accommodates 2 electrons. The next 2 electrons occupy 2s orbital. These 2 electrons cannot occupy 2p orbital because 2p orbital is higher energy than 2s orbital. The last, the 5th electron occupy 2p orbital. The second rule used to assign electron into orbitals is Pauli Exclusion principle. Pauli Exclusion principle states that no 2 electrons in an atom can have the same 4 quantum numbers N, L, M, S. Let's determine 4 quantum number of 2 electrons in helium as example. 2 electrons with opposite rotation occupy in 1s orbital. These 2 electrons will have this set 4 quantum number. Since electron A and B have different electron spin quantum number, positive half and negative half, they obey Pauli exclusion principle. Let's say 2 electrons occupy in 1s orbital like this arrangement. C electron and D electron have same electron spin, rotation. If electron spin quantum number for C electron is positive half, D electron also positive half. C electron and D electron have same 4 quantum number, which is 1, 0, 0, positive half. So it does not obey Pauli exclusion principle. E electron and F electron has similar electron spin rotation. Thus, they have similar electron spin quantum number, which is negative half. E electron and F electron has similar 4 quantum number, which is 1, 0, 0, negative half. So it does not obey Pauli exclusion principle. The third rule assigning electrons in orbital is Hund's rule. Hund's rule states that when electrons are added to the orbital of equivalent energy or degenerate orbitals, each orbitals are filled singly with electrons of the parallel spins or same first before it is paired. Let's use nitrogen, which has 7 electrons, to apply the Hund's rule. Consider these two electronics configuration. The above configuration obey the Hund's rule because all 3 degenerated 2p orbitals are filled singly parallel spin electron. But below's configuration does not obey Hund's rule because there is empty orbital. At the same time, 2 electrons occupy the same orbital. In addition, this electron has different rotation compared to these 2 electrons. In other words, these 3 electrons in the degenerated 2p orbital are not in the parallel spins. For conclusion, this configuration is allowed while this configuration is not allowed. So, we have finished discuss 3 rules used to assign electronics configuration. Now, we continue our next lesson, which is the anomalous electronics configuration of copper and chromium. Copper and chromium have electrons configuration which are inconsistent with Aufbau principle. Inconsistent with Aufbau principle because of fully filled or half-filled orbital is more stable than partially filled orbital. Let's study the anomalous case of copper. So this is expected configuration of copper by applying Aufbau principle. 4s orbital is fully filled orbital while 3d orbital is partially filled orbital. But this is actual configuration of copper. We can see that 3d orbital is fully filled while 1 electron at the 4s orbital. This happens because 1 electron in 4s subshell is promoted to occupy fully 3d subshell. And the anomalous filling pattern is due to the stability of the completely or fully filled 3d10 subshell. Let's continue with the anomalous case chromium. So this is expected configuration for the chromium. We can see that 4 electrons occupy at the 3d orbital. But this is the actual configuration. What really happened is 1 electron in 4s subshell is promoted to occupy partially 3d subshell. As a result, half-filled 3d5 orbital is formed. This half-filled 3d5 orbital is stable. Before ending our lesson, please do this exercise. Proton number for element A and B are 16 and 24 respectively. Write electronic configuration for A and B. So we have finished our lesson. Thanks for watching and see you around.